This is a photo of change, a set of keys in a pile. There appear to be 5 pennies, 3 quarters, 4 dimes, and 2 nickels. The key ring has a bronze whale on it and holds 11 keys. Figure 7. 1. If you want to figure out the distribution of the change people carry in their pockets, using the central limit theorem and assuming your sample is large enough, you will find that the distribution is normal and bell-shaped. Credit. Modification of work, American Coins by Paula R. Lively Flickr, CC by 20. Chapter Objectives. By the end of this chapter, the student should be able to recognize central limit theorem problems, classify continuous word problems by their distributions, apply and interpret the central limit theorem for means, apply and interpret the central limit theorem for sums. Why are we so concerned with means? 2 reasons are: they give us a middle ground for comparison and they are easy to calculate. In this chapter, you will study means and the central limit theorem. The central limit theorem, CLT for short, is one of the most powerful and useful ideas in all of statistics. There are 2 alternative forms of the theorem, and both alternatives are concerned with drawing finite samples, size n, from a population with a known mean, mu, and a known standard deviation, sigma. The first alternative says that if we collect samples of size n with a large enough n, calculate each sample's mean, and create a histogram of those means, then the resulting histogram will tend to have an approximate normal bell shape. The second alternative says that if we again collect samples of size n that are large enough, calculate the sum of each sample, and create a histogram, then the resulting histogram will again tend to have a normal bell shape. The size of the sample, n, that is required in order to be large enough, depends on the original population from which the samples are drawn. The sample size should be at least 30, or the data should come from a normal distribution. If the original population is far from normal, then more observations are needed for the sample means, or sums, to be normal. Sampling is done with replacement. It would be difficult to overstate the importance of the central limit theorem in statistical theory. Knowing that data, even if its distribution is not normal, behaves in a predictable way is a powerful tool. Collaborative exercise. Suppose 8 of you roll 1 fair die 10 times, 7 of you roll 2 fair dice 10 times, 9 of you roll 5 fair dice 10 times, and 11 of you roll 10 fair dice 10 times. Each time a person rolls more than 1 die, they calculate the sample mean of the faces showing. For example, one person might roll 5 fair dice and get 2, 2, 3, 4, 6 on one roll. The mean is 2 plus 2 plus 3 plus 4 plus 65 equals 3 4. The 3 4 is one mean when 5 fair dice are rolled. This same person would roll the 5 dice 9 more times and calculate 9 more means for a total of 10 means. Your instructor will pass out the dice to several people. Roll your dice 10 times. For each roll, record the faces and find the mean. Round to the nearest 0, 5. Your instructor and possibly you will produce one graph. It might be a histogram for 1 die, 1 graph for 2 dice, 1 graph for 5 dice, and 1 graph for 10 dice. Since the mean, when you roll 1 die, is just the face on the die, what distribution do these means appear to be representing? Draw the graph for the means using 2 dice. Do the sample means show any kind of pattern? Draw the graph for the means using 5 dice. Do you see any pattern emerging? Finally, draw the graph for the means using 10 dice. Do you see any pattern to the graph? What can you conclude as you increase the number of dice? As the number of dice rolled increases from 1 to 2 to 5 to 10, the following is happening. The mean of the sample means remains approximately the same. The spread of the sample means, the standard deviation of the sample means, gets smaller. The graph appears steeper and thinner. You have just demonstrated the central limit theorem, CLT. The central limit theorem tells you that as you increase the number of dice, the sample means tend toward a normal distribution, the sampling distribution. Suppose x is a random variable with a distribution that may be known or unknown. It can be any distribution. Using a subscript that matches the random variable, suppose mu x equals the mean of x, sigma x equals the standard deviation of x. If you draw random samples of size n, then as n increases, the random variable letter 1d465, which consists of sample means, tends to be normally distributed and letter 1d44b tilde, letter 1d441, letter 1d707, letter 1d465, letter 1d70e, letter 1d44b, letter 1d45b square root. The central limit theorem for sample means says that if you repeatedly draw samples of a given size, such as repeatedly rolling 10 dice, and calculate their means, those means tend to follow a normal distribution, the sampling distribution. As sample sizes increase, the distribution of means more closely follows the normal distribution. The normal distribution has the same mean as the original distribution, and a variance that equals the original variance divided by the sample size. Standard deviation is the square root of variance, so the standard deviation of the sampling distribution is the standard deviation of the original distribution divided by the square root of n. The variable n is the number of values that are averaged together, not the number of times the experiment is done. To put it more formally, if you draw random samples of size n, the distribution of the random variable letter 1d44b, which consists of sample means, is called the sampling distribution of the mean. The sampling distribution of the mean approaches a normal distribution as n, the sample size, increases. The random variable letter 1d44b has a different z-score associated with it from that of the random variable x. The mean letter 1d465 is the value of letter 1d44b. In one sample, letter 1d467 equals letter 1d465 minus letter 1d707, letter 1d465, letter 1d70e, letter 1d44b, letter 1d45b square root. Mu x is the average of both x and letter 1d44b. Letter 1d70e, letter 1d465 equals letter 1d70e, letter 1d44b, letter 1d45b square equals standard deviation of letter 1d44b, and is called the standard error of the mean. Using the T83, 83 plus 84, 84 plus calculator. To find probabilities for means on the calculator, follow these steps. Second, DISTR. 2. Normalkjif. Letter 1d45b, letter 1d45c, letter 1d45f, letter 1d45a, letter 1d44e, letter 1d459. Letter 1d459, letter 1d45c, letter 1d464, letter 1d452, letter 1d45f. Value of the area. Upper value of the area. Mean. Standard letter 1d451, letter 1d452, letter 1d463, letter 1d456, letter 1d44, letter 1d461, letter 1d460, letter 1d456, letter 1d467, letter 1d452, square root. Where mean is the mean of the original distribution. Standard deviation is the standard deviation of the original distribution. Sample size equals n. Example 7. 1. An unknown distribution has a mean of 90 and a standard deviation of 15. Samples of size n equals 25 are drawn randomly from the population. Problem. They find the probability that the sample mean is between 85 and 92. Solution. A. Let x equals one value from the original unknown population. The probability question asks you to find a probability for the sample mean. Let letter 1d465 equals the mean of a sample of size 25. Since mu x equals 90, sigma x equals 15, and n equals 25. Letter 1d465. N 90, 1525 square root. Find p, 85, letter 1d465. 92, draw a graph. P 85, letter 1d465. 92 equals 0. 6997. The probability that the sample mean is between 85 and 92 is 0. 6997. This is a normal distribution curve. The peak of the curve coincides with the point 90 on the horizontal axis. The points 85 and 92 are labeled on the axis. Vertical lines are drawn from these points to the curve, and the area between the lines is shaded. The shaded region represents the probability that 85x 92, figure 7. 2. Using the T83, 83 plus 84, 84 plus calculator. Normocht lower value, upper value mean, standard error of the mean. The parameter list is abbreviated lower value, upper value, mu, letter 1D70, letter 1D45B square root. Normocht 85, 92, 90, 1525 square root equals 0. 6997. Problem. B. Find the value that is 2 standard deviations above the expected value 90 of the sample mean. Solution. B. To find the value that is 2 standard deviations above the expected value 90. Use the formula. Value equals mux of TSDVs. Letter 1D70, letter 1D465, letter 1D45B square root. Value equals 90 plus 2, 1525 square root, equals 96. The value that is 2 standard deviations above the expected value is 96. The standard error of the mean is letter 1D70, letter 1D465, letter 1D45B square root, equals 1525 square root, equals 3. Recall that the standard error of the mean is a description of how far, on average, that the sample mean will be from the population mean in repeated simple random samples of size n. Try it 7. 1. An unknown distribution has a mean of 45 and a standard deviation of 8. Samples of size n equals 30 are drawn randomly from the population. Find the probability that the sample mean is between 42 and 50. Example 7.2. Problem. The length of time in hours it takes an over 40 group of people to play one soccer match is normally distributed with a mean of 2 hours and a standard deviation of 0. 5 hours. A sample of size n equals 50 is drawn randomly from the population. Find the probability that the sample mean is between 18 hours and 23 hours. Solution. Let x equals the time in hours it takes to play one soccer match. The probability question asks you to find a probability for the sample mean time in hours it takes to play one soccer match. Let letter 1D465 equals the mean time in hours it takes to play one soccer match. If mu x equals, sigma x equals, and n equals, then letter 1D44b. N, by the central limit theorem for means. Mu x equals 2, sigma x equals 0.5, n equals 50, and xn, 2, 0. 550 square root. Find P1, 8 letter 1D465. 2, 3, draw graph P1. 8 letter 1D465. 2, 3 equals 0. 9977. Normocht 1, 82, 32, 550 square root. Equals 0. 9977. The probability that the mean time is between 18 hours and 23 hours is 0. 9977. Try it 7.2. The length of time taken on the SAT for a group of students is normally distributed with a mean of 2. 5 hours and a standard deviation of 0.25 hours. A sample size of n equals 60 is drawn randomly from the population. Find the probability that the sample mean is between 2 hours and 3 hours. Using the T83, 83 plus 84, 84 plus calculator. To find percentiles for means on the calculator, follow these steps. Second, dice and R. 3. Inv norm. K equals inv norm, area to the left of K mean. Standard letter 1D451, letter 1D452, letter 1D463, letter 1D456, letter 1D440, letter 1D461, letter 1D460, letter 1D456, letter 1D467, letter 1D452, square root. Where K equals the kth percentile. Mean is the mean of the original distribution. Standard deviation is the standard deviation of the original distribution. Sample size equals n. Example 7. 3. Problem. In a recent study, it was reported that the mean age of iPad users is 34 years. Suppose the standard deviation is 15 years. Take a sample of size n equals 100. What are the mean and standard deviation for the sample mean ages of iPad users? What does the distribution look like? Find the probability that the sample mean age is more than 30 years, the reported mean age of iPad users in this particular study. Find the 95th percentile for the sample mean age to one decimal place. Solution. Since the sample mean tends to target the population mean, we have mu chi equals mu equals 34. The sample standard deviation is given by sigma chi equals letter 1d70 letter 1d45b square root equals 15,100 square root equals 1,510 equals 1. 5. The central limit theorem states that for large sample sizes, n, the sampling distribution will be approximately normal. The probability that the sample mean age is more than 30 is given by letter 1d443, letter 1d44b 30, equals normoct 30, E9934 1. 5 equals 09962. Let k equals the 95th percentile. K equals inv norm 0.9534, 15,100 square root equals 36. 5. Try it 7.3. In an article on Flurry blog, a gaming marketing gap for men between the ages of 30 and 40 is identified. You are researching a startup game targeted at the 35-year-old demographic. Your idea is to develop a strategy game that can be played by men from their late 20s through their late 30s. Based on the article's data, industry research shows that the average strategy player is 28 years old with a standard deviation of 4. 8 years. You take a sample of 100 randomly selected gamers. If your target market is 29 to 35-year-olds, should you continue with your development strategy? Example 7. 4. Problem. The mean number of minutes for app engagement by an iPad user is 82 minutes. Suppose the standard deviation is 1 minute. Take a sample of 60. What are the mean and standard deviation for the sample mean number of minutes for app engagement by an iPad user? What is the standard error of the mean? Find the 90th percentile for the sample mean time of minutes for app engagement by an iPad user. Interpret this value in a complete sentence. Find the probability that the sample mean is between 8 minutes and 85 minutes. Solution. Letter 1d707 letter 1d465 equals letter 1d707 equals 8. 2. Letter 1d70 letter 1d465 equals letter 1d70 letter 1d45b square equals 160 square equals 0. 13. This allows us to calculate the probability of sample means of a particular distance from the mean in repeated samples of size 60. Let k equals the 90th percentile. K equals inv norm 0. 908 to 160 square root equals 837. This values indicates that 90% of the average app engagement time for iPad users is less than 37 minutes. P8 letter 1d465. 85 equals normoct 88, 58 to 160 square root equals 0, 92, 93. Try it 7. 4. Cans of a cola beverage claim to contain 16 ounces. The amounts in a sample are measured, and the statistics are n equals 34, letter 1d465, equals 16, 1 ounces. If the cans are filled so that mu equals 16, 0 ounces, as labeled, and sigma equals 0, 143 ounces, find the probability that a sample of 34 cans will have an average amount greater than 16. 1 ounces. Do the results suggest that cans are filled with an amount greater than 16 ounces? Suppose X is a random variable with a distribution that may be known or unknown. It can be any distribution, and suppose mu x equals the mean of chi sigma chi equals the standard deviation of x if you draw random samples of size n. Then as n increases, the random variable sigmax consisting of sums tends to be normally distributed and sigma chi n mu chi letter 1d45b square root sigma chi. The central limit theorem for sums says that if you repeatedly draw samples of a given size, such as repeatedly rolling 10 dice, and calculate the sum of each sample, these sums tend to follow a normal distribution. As sample sizes increase, the distribution of means more closely follows the normal distribution. The normal distribution has a mean equal to the original mean multiplied by the sample size, and a standard deviation equal to the original standard deviation multiplied by the square root of the sample size. The random variable sigmax has the following z-score associated with it. Sigmax is one sum. Z equals letter 1d6f4, letter 1d465, letter 1d45b, letter 1d707, letter 1d44b, letter 1d45b square root, letter 1d70e, letter 1d44b. N, mu x, equals the mean of sigmax, letter 1d45b square root, letter 1d70e, letter 1d44b, equals standard deviation of letter 1d6f4, letter 1d44b using the T83. 83 plus 84, 84 plus calculator to find probabilities for sums on the calculator. Follow these steps. Second DISTR2, Normaltf, lower value of the area, upper value of the area, n, mean, letter 1d45b square root, standard deviation, where mean is the mean of the original distribution, standard deviation is the standard deviation of the original distribution sample, size equals n. Example 7. 5. An unknown distribution has a mean of 90 and a standard deviation of 15. A sample of size 80 is drawn randomly from the population. Problem: find the probability that the sum of the 80 values, or the total of the 80 values, is more than 7,500. Find the sum that is 1/5 standard deviations above the mean of the sums. Solution: let x equals one value from the original unknown population. The probability question asks you to find a probability for the sum or total of 80 values. Sigmax equals the sum or total of 80 values. Since mu x equals 90, sigma x equals 15, and n equals 80, letter 1d6f4, letter 1d44b, n, 80, 90. 80 square 15. Mean of the sums equals n, mu x equals 7. 200 standard deviation of the sums equals letter 1d45b square root, letter 1d70e, letter 1d44b, equals 80 square 15. Sum of 80 values equals sigmax equals 7. 500a. Find p, sigmax 7,500, p, sigmax 7,500 equals 0. 127. This is a normal distribution curve. The peak of the curve coincides with the point 7200 on the horizontal axis. The point 7500 is also labeled. A vertical line extends from point 7500 to the curve. The area to the right of 7500 below the curve is shaded. Figure 7. 3. Using the T83, 83 plus 84, 84 plus calculator normal, lower value, upper value, mean of sums, stdev of sums. The parameter list is abbreviated lower, upper, n, mu x, letter 1d45b square root, sigma x, normal 7,500, 1e99, 80, 90, 80 square 15 equals 0. 127. Reminder: 1e99 equals 1099. Press the EE key for EB. Find sigmax where z equals 15. Sigmax equals n, mu x, plus z, letter 1d45b square root, sigma chi, a plus 1. 5. 80 square 15 equals 7,401. 2 try its 7.5. An unknown distribution has a mean of 45 and a standard deviation of 8. A sample size of 50 is drawn randomly from the population. Find the probability that the sum of the 50 values is more than 2,400. Using the T83, 83 plus 84, 84 plus calculator to find percentiles for sums on the calculator. Follow these steps. Second dicent R3. Inv norm K equals inv norm area to the left of K, N, mean, letter 1 D45B square root, standard deviation, where K is the KTH percentile mean, is the mean of the original distribution standard deviation, is the standard deviation of the original distribution sample, size equals N. Example 7. 6. Problem. In a recent study, it was reported that the mean age of iPad users is 34 years. Suppose the standard deviation is 15 years. The sample of size is 50. What are the mean and standard deviation for the sum of the ages of iPad users? What is the distribution? Find the probability that the sum of the ages is between 1,500 and 1,800 years. Find the 80th percentile for the sum of the 50 ages. Solution mu sigmax equals n mux equals 50, 34, equals 1,700, and sigma sigmax equals letter 1 D45B square root sigmax equals 50 square, 15, equals 106. 7. The distribution is normal for sums by the central limit theorem. P 1,500 sigmax 1,800 equals normoct 1,500, 1,800, 50, 34, 50 square 15 equals 0. 7974. Let K equals the 80th percentile. K equals inv norm 0. 80, 50, 34, 50 square 15 equals 1,789. 3 try it 7. 6. In a recent study, it was reported that the mean age of iPad users is 35 years. Suppose the standard deviation is 10 years. The sample size is 39. What are the mean and standard deviation for the sum of the ages of iPad users? What is the distribution? Find the probability that the sum of the ages is between 1,400 and 1,500 years. Find the 90th percentile for the sum of the 39 ages. Example 7.7 problem. The mean number of minutes for app engagement by a tablet user is 82 minutes. Suppose the standard deviation is 1 minute. Take a sample of size 70. What are the mean and standard deviation for the sums? Find the 95th percentile for the sum of the sample. Interpret this value in a complete sentence. Find the probability that the sum of the sample is at least 10 hours. Solution mu sigmax equals n mux equals 78. 2 equals 574 minutes and sigma sigmax equals letter 1 D45B square root. Letter 1 D70 letter 1 D465 equals 70 square 1 equals 8. 37 minutes. Let K equals the 95th percentile. K equals inv norm 0. 95, 70, 8, 2, 70 square 1 equals 587. 76 minutes. 95% of the sums of app engagement times are at most 587. 76 minutes. 10 hours equals 600 minutes. P sigmax greater or equal to 600. Normoct 600 E99 70. 8. 2, 70 square 1 equals 0. 9 try it 7. 7. The mean number of minutes for app engagement by a table use is 82 minutes. Suppose the standard deviation is 1 minute. Take a sample size of 70. What is the probability that the sum of the sample is between 7 hours and 10 hours? What does this mean in context of the problem? Find the 84th and 16th percentiles for the sum of the sample. Interpret these values in context. It is important for you to understand when to use the central limit theorem. If you are being asked to find the probability of the mean, use the CLT for the mean. If you are being asked to find the probability of a sum or total, use the CLT for sums. This also applies to percentiles for means and sums. Note, if you are being asked to find the probability of an individual value, do not use the CLT. Use the distribution of its random variable. Examples of the central limit theorem, law of large numbers. The law of large numbers says that if you take samples of larger and larger size from any population, then the mean letter 1d465 of the sample tends to get closer and closer to mu. From the central limit theorem, we know that as n gets larger and larger, the sample means follow a normal distribution. The larger n gets, the smaller the standard deviation gets. Remember that the standard deviation for letter 1d44b is letter 1d70 letter 1d45b square root. This means that the sample mean letter 1d465 must be close to the population mean mu. We can say that mu is the value that the sample means approach as n gets larger. The central limit theorem illustrates the law of large numbers. Central limit theorem for the mean and sum examples. Example 7. 8. A study involving stress is conducted among the students on a college campus. The stress scores follow a uniform distribution, with the lowest stress score equal to 1 and the highest equal to 5. Using a sample of 75 students, find the probability that the mean stress score for the 75 students is less than 2. The 90th percentile for the mean stress score for the 75 students. The probability that the total of the 75 stress scores is less than 200. The 90th percentile for the total stress score for the 75 students. Let X equals 1 stress score. Problems A and B ask you to find a probability or a percentile for a mean. Problems C and D ask you to find a probability or a percentile for a total or sum. The sample size, n, is equal to 75. Since the individual stress scores follow a uniform distribution, XU, 1, 5, where a 1 and B equals 5, see continuous random variables for an explanation on the uniform distribution. Mu x equals a plus b2 equals 1 plus 52 equals 3 sigma x equals letter 1d44f letter 1d44e. 212 square equals 5 1 212 square equals 1612 square equals 43 square, or approximately 1. 15. For problems A and B, let letter 1d44b equals the mean stress score for the 75 students. Then, letter 1d44b n3, 1575 square root, problem A. Find P, letter 1d4652. Draw the graph. Solution AP, letter 1d4652, equals the probability that the mean stress score is less than 2 is about 0. This is a normal distribution curve over a horizontal axis. The peak of the curve coincides with the point 3 on the horizontal axis. A point 2 is marked at the left edge of the curve. Figure 7. For Normalkt, 1231. 1575 square root equals 0. Reminder: the smallest stress score is 1. Problem B. Find the 90th percentile for the mean of 75 stress scores. Draw a graph. Solution B. Let K equals the 90th percentile. Find K, where P, letter 1d465 K, equals 0.90. K equals 3.2. This is a normal distribution curve. The peak of the curve coincides with the point 3 on the horizontal axis. A point, K, is labeled to the right of 3. A vertical line extends from K to the curve. The area under the curve to the left of K is shaded. The shaded area shows that P, x bar K, equals 0.90. Figure 7.5. The 90th percentile for the mean of 75 scores is about 3.2. This tells us that 90% of all the means of 75 stress scores are at most 3.2, and that 10% are at least 3.2. Inv norm, 9031. 1575 square root equals 3.2 for problems C and D. Let sigmix equals the sum of the 75 stress scores. Then, sigmix tilde n, 75, 3, 75 square, 1. 15. Problem C. Find P. Sigmix 200. Draw the graph. Solution C. The mean of the sum of 75 stress scores is 75. 3 equals 225. The standard deviation of the sum of 75 stress scores is 75 square. 43 square equals 75 times 43 square equals 100 square equals 10p. Sigmix 200 equals 0. 62. This is a normal distribution curve over a horizontal axis. The peak of the curve coincides with the point 225 on the horizontal axis. A point 200 is marked at the left edge of the curve. Figure 7.6. The probability that the total of 75 scores is less than 200 is about 0.62. Normelkt 75 200, 75, 3. Reminder: the smallest total of 75 stress scores is 75 because the smallest single score is 1. Problem D. Find the 90th percentile for the total of 75 stress scores. Draw a graph. Solution D. Let K equals the 90th percentile. Find K where P, sigmix K, equals 0.90. K equals 237. 8. This is a normal distribution curve. The peak of the curve coincides with the point 225 on the horizontal axis. A point K is labeled to the right of 225. A vertical line extends from K to the curve. The area under the curve to the left of K is shaded. The shaded area shows that P, sum of xk, equals 0. 90. Figure 7.7. The 90th percentile for the sum of 75 scores is about 237.8. This tells us that 90% of all the sums of 75 scores are no more than 237. 8 and 10% are no less than 237.8. Inv norm. 90, 75, 3, 75 square, 115, equals 237. 8. Try it. 7. 8. Use the information in example 7.8 but use a sample size of 55 to answer the following questions. Find P, letter 1 D465 7. Find P, sigmix 170. Find the 80th percentile for the mean of 55 scores. Find the 85th percentile for the sum of 55 scores. Example 7. 9. Suppose that a market research analyst for a cell phone company conducts a study of their customers who exceed the time allowance included on their basic cell phone contract. The analyst finds that for those people who exceed the time included in their basic contract, the excess time used follows an exponential distribution with a mean of 22 minutes. Consider a random sample of 80 customers who exceed the time allowance included in their basic cell phone contract. Let X equals the excess time used by one individual cell phone customer who exceeds his contracted time allowance. XX 122. From previous chapters, we know that mu equals 22 and sigma equals 22. Let letter 1 D44b equals the mean excess time used by a sample of n equals 80 customers who exceed their contracted time allowance. Letter 1 D44b, n, 22, 2280 square root. By the central limit theorem for sample means problem using the CLT to find probability. Find the probability that the mean excess time used by the 80 customers in the sample is longer than 20 minutes. This is asking us to find P, letter 1 D465 20. Draw the graph. Suppose that one customer who exceeds the time limit for his cell phone contract is randomly selected. Find the probability that this individual customer's excess time is longer than 20 minutes. This is asking us to find P, x 20. Explain why the probabilities in parts A and B are different. Solution: find P, letter 1 D465 20. P, letter 1 D465 20 equals 0.79199 using Normelkt 20, 1e99 22, 2280 square root. The probability is 0.7919 that the mean excess time used is more than 20 minutes. for a sample of 80 customers who exceed their contracted time allowance. This is a normal distribution curve. The peak of the curve coincides with the point 22 on the horizontal axis. A point, 20, is labeled to the left of 22. A vertical line extends from 20 to the curve. The area under the curve to the right of K is shaded. The shaded area shows that P, x bar 20. Figure 7.8 reminder 1E99 equals 1099 and 1E99 equals 1099. Press the EA key for E or just use 1099 instead of 1E99. Find P, x20. Remember to use the exponential distribution for an individual. Letter 1D44B tilde, letter 1D438, letter 1D465, letter 1D45D, 122. Letter 1D443, letter 1D465, 20, letter 1D452 minus, 122, 20, or E0. 04545, 20 equals 0. 4029 P x 20 equals 0 4029 but P, letter 1D465, 20 equals 0. 7919. The probabilities are not equal because we use different distributions to calculate the probability for individuals and for means. When asked to find the probability of an individual value, use the stated distribution of its random variable. Do not use the CLT. Use the CLT with the normal distribution when you are being asked to find the probability for a mean. Problem using the CLT to find percentiles. Find the 95th percentile for the sample mean excess time for samples of 80 customers who exceed their basic contract time allowances. Draw a graph. Solution: let K equals the 95th percentile. Find K where P, letter 1D465K, equals 0. 95K equals 26. 0 using inv norm 0. 95, 22, 2280 square root equals 26. This is a normal distribution curve. The peak of the curve coincides with the point 22 on the horizontal axis. A point K is labeled to the right of 22. A vertical line extends from K to the curve. The area under the curve to the left of K is shaded. The shaded area shows that P, x bar K, equals 0.95. Figure 7. 9. The 95th percentile for the sample mean excess time used is about 26. 0 minutes for random samples of 80 customers who exceed their contractual allowed time. 95% of such samples would have means under 26 minutes. Only 5% of such samples would have means above 26 minutes. Try it 7. 9. Use the information in example 7. 9 but change the sample size to 144. Find P, 20, letter 1D465, 30. Find P, sigmix is at least 3000. Find the 75th percentile for the sample mean excess time of 144 customers. Find the 85th percentile for the sum of 144 excess times used by customers. Example 7. 10. In the United States, a robbery occurs every 2 minutes on average, according to a number of studies. Suppose the standard deviation is 0.5 minutes and the sample size is 100. Problem: find the median, the first quartile, and the third quartile for the sample mean time of robberies in the United States. Find the median, the first quartile, and the third quartile for the sum of sample times of robberies in the United States. Find the probability that a robbery occurs on the average between 175 and 185 minutes. Find the value that is 2 standard deviations above the sample mean. Find the IQR for the sum of the sample times. Solution: we have mux equals mu equals 2 and sigmix equals letter 1D70 letter 1D45B square root equals 0 510 equals 0. 5. Therefore, 50th percentile equals mux equals mu equals 2. 25th percentile equals inv norm 0. 2520. 5 equals 1. 97 75th percentile equals inv norm 0. 5 equals 2, 3, we have mu sigmix equals n, mux equals 102, equals 200, and sigma mux equals letter 1 d4 5b square root sigmix equals 10, 0. 5 equals 5. Therefore 50th percentile equals mu sigmix equals n, mux equals 102, equals 225th percentile equals inv norm 0. 252,005 equals 196. 63 75th percentile equals inv norm 0. 752,005 equals 203. 37p 1. 75 letter 1 d465 1. 85 normalct 1. 751. 8,520. 5 equals 0. 13 using the z-score equation. Z equals letter 1 d465, letter 1 d707, letter 1 d465, letter 1 d70, letter 1 d465. And solving for x, we have x equals 2, 0. 5 plus 2 equals 2, 1. The IQR is 75th percentile. 25th percentile equals 203. 37, 196. 63 equals 6. 74 try it 7. 10 based on data from the National Health Survey, females between the ages of 18 and 24 have an average systolic blood pressures in Hg of 114, 8 with a standard deviation of 13. 1 systolic blood pressure for females between the ages of 18 to 24 follow a normal distribution. If one female from this population is randomly selected, find the probability that their systolic blood pressure is greater than 120. If 40 females from this population are randomly selected, find the probability that their mean systolic blood pressure is greater than 120. If the sample were 4 females between the ages of 18 to 24, and we did not know the original distribution, could the central limit theorem be used? Example 7.11 problem. A study was done regarding attendance at Broadway shows in New York City. The age range of the attendees was 14 to 61. The mean age was 30. 9 years with a standard deviation of 9 years. In a sample of 25 attendees, what is the probability that the mean age is less than 35? Is it likely that the mean age of the sample group could be more than 50 years? Interpret the results. In a sample of 49 attendees, what is the probability that the sum of the ages is no less than 1,600? Is it likely that the sum of the ages of the 49 attendees is at most 1,595? Interpret the results. Find the 95th percentile for the sample mean age of 65 attendees. Interpret the results. Find the 90th percentile for the sum of the ages of 65 attendees. Interpret the results. Solution P, letter 1 d465 35, equals normalct E99 35 30. 91. 8 equals 0. 98 86 P, letter 1 d465 50, equals normalct 50, E9930. 91. 8 approximately 0. For this sample group, it is almost impossible for the group's average age to be more than 50. However, it is still possible for an individual in this group to have an age greater than 50. P sigmix greater or equal to 1,600 equals normalct 1,600 E99 1,514. 1,063 equals 0. 864 P sigmix less or equal to 1,595 equals normalct E99 1,595 1,514. 1,063 equals 0. 9,005. This means that there is a 90% chance that the sum of the ages for the sample group N equals 49 is at most 1595. The 95th percentile equals inv norm 0, 9,530, 91. 1 equals 32. 7. This indicates that 95% of the attendees in the sample of 65 are younger than 32. 7 years on average. The 90th percentile equals inv norm 0, 902,008, 572, 56, equals 2101, 5. This indicates that 90% of the attendees in the sample of 65 have a sum of ages less than 2,101, 5 years. Try at 7-Eleven. According to Boeing data, the 757 airliner carries 200 passengers and has doors with a height of 72 inches. Assume for a certain population of men we have a mean height of 69.0 inches and a standard deviation of 28 inches. What doorway height would allow 95% of men to enter the aircraft without bending? Assume that half of the 200 passengers are men. What mean doorway height satisfies the condition that there is a 0.95 probability that this height is greater than the mean height of 100 men? For engineers designing the 757, which result is more relevant? The height from Part O or Part B? Why? Historical note: normal approximation to the binomial. Historically, being able to compute binomial probabilities was one of the most important applications of the central limit theorem. Binomial probabilities with a small value for n, say 20, were displayed in a table in a book. To calculate the probabilities with large values of n, you had to use the binomial formula, which could be very complicated. Using the normal approximation to the binomial distribution simplified the process. To compute the normal approximation to the binomial distribution, take a simple random sample from a population. You must meet the conditions for a binomial distribution. There are a certain number n of independent trials. The outcomes of any trial are success or failure. Each trial has the same probability of a success p. Recall that if x is the binomial random variable, then x b, n, p. The shape of the binomial distribution needs to be similar to the shape of the normal distribution. To ensure this, the quantities np and nq must both be greater than 5, np5 and nq5. The approximation is better if they are both greater than or equal to 10. Then the binomial can be approximated by the normal distribution with mean mu equals np and standard deviation sigma equals letter 1d45b letter 1d45d letter 1d45e square. Remember that q equals 1p. In order to get the best approximation, add 0.5 to x or subtract 0.5 from x. Use x plus 0.5 or x 0.5. The number 0.5 is called the continuity correction factor and is used in the following example. Example 712. Suppose in a local kindergarten through 12th grade, K-12, school district, 53% of the population favor a charter school for grades K through 5. A simple random sample of 300 is surveyed. Find the probability that at least 150 favor a charter school. Find the probability that at most 160 favor a charter school. Find the probability that more than 155 favor a charter school. Find the probability that fewer than 147 favor a charter school. Find the probability that exactly 175 favor a charter school. Let x equals the number that favor a charter school for grades K-5. xbn, p, where n equals 300 and p equals 0.53. Since np5 and nq5 use the normal approximation to the binomial, the formulas for the mean and standard deviation are mu equals np and sigma equals letter 1d45b letter 1d45d letter 1d45e square. The mean is 159 and the standard deviation is 8.6447. The random variable for the normal distribution is yn, 159, 8.6447. See the normal distribution for help with calculator instructions. For part A, you include 150 so p, x greater or equal to 150, has normal approximation p, y greater or equal to 149. 5 equals 0.8641, normalct 149. 5, 1099, 159, 8. 6447 equals 08641. For part B, you include 160, so p, x less or equal to 160, has normal approximation p, y less or equal to 160. 5 equals 05689. Normalct 0, 160. 51,598. 6447 equals 05689. For part C, you exclude 155, so p, x 155, has normal approximation p, y 155. 5 equals 0. 6572. Normalct 155. 5, 1099, 159, 8. 6447 equals 0. 6572. For part D, you exclude 147, so p, x 147, has normal approximation p, y 146, 5 equals 0. 741. Normalct 0, 146. 51,598. 6447 equals 0. 741. For part E, p, x equals 175, has normal approximation p, 174. 5y 175, 5 equals 0. 83. Normalct 174. 5,175. 51,598. 6447 equals 083 because of calculators and computer software that let you calculate binomial probabilities for large values of n easily. It is not necessary to use the normal approximation to the binomial distribution, provided that you have access to these technology tools. Most school labs have Microsoft Excel, an example of computer software that calculates binomial probabilities. Many students have access to the T83 or 84 series calculators, and they easily calculate probabilities for the binomial distribution. If you type in binomial probability distribution calculation in an internet browser, you can find at least one online calculator for the binomial. For example, 7. 12. The probabilities are calculated using the following binomial distribution. N equals 300 and p equals 0.53. Compare the binomial and normal distribution answers. See discrete random variables for help with calculator instructions for the binomial. P, x greater or equal to 150. 1 binomialct 300 0. 53,149 equals 0.8641. P, x less or equal to 160. Binomial 300 0. 53,160 equals 0. 5684. P, x 155. 1 binomial 300 0. 53,155 equals 0. 6576. P, x 147. Binomial 300 0. 53,146 equals 0. 742. P, x equals 175. You use the binomial PDF. Binomial 300 0. 53,175 equals 0.83. Try it. 712. In a city, 46% of the population favor the incumbent, Don Morgan, for mayor. A simple random sample of 500 is taken. Using the continuity correction factor, find the probability that at least 250 favor Don Morgan for mayor. Stats Lab. Central Limit Theorem, Pocket Chain. Class time, names, student learning outcomes. The student will demonstrate and compare properties of the central limit theorem. Note, this lab works best when sampling from several classes and combining data. Collect the data. Count the change in your pocket. Do not include bills. Randomly survey 30 classmates. Record the values of the change in Table 7. 1. Table 7.1. Construct a histogram. Make 5 to 6 intervals. Sketch the graph using a ruler and pencil. Scale the axes. Blank graph template. The horizontal axis is labeled value of the change and the vertical axis is labeled frequency. Figure 710. Calculate the following: n equals 1, surveying one person at a time. Letter 1D465. Equals. S equals. Draw a smooth curve through the tops of the bars of the histogram. Use 1 to 2 complete sentences to describe the general shape of the curve. Collecting averages of pairs. Repeat steps 1 through 5 of the section. Collect the data, with one exception. Instead of recording the change of 30 classmates, record the average change of 30 pairs. Randomly survey 30 pairs of classmates. Record the values of the average of their change in Table 7 to Table 7. 2. Construct a histogram. Scale the axes using the same scaling you used for the section titled Collect the Data. Sketch the graph using a ruler and a pencil. This is a blank graph template. The horizontal axis is labeled value of the chain, and the vertical axis is labeled frequency. Figure 711. Calculate the following: n equals 2, surveying 2 people at a time. Letter 1D465. Equals. S equals. Draw a smooth curve through tops of the bars of the histogram. Use 1 to 2 complete sentences to describe the general shape of the curve. Collecting averages of groups of 5. Repeat steps 1 through 5 of the section titled Collect the Data, with one exception. Instead of recording the change of 30 classmates, record the average change of 30 groups of 5. Randomly survey 30 groups of 5 classmates. Record the values of the average of their change. Table 7.3. Construct a histogram. Scale the axes using the same scaling you used for the section titled Collect the Data. Sketch the graph using a ruler and a pencil. This is a blank graph template. The horizontal axis is labeled value of the chain, and the vertical axis is labeled frequency. Figure 7.12. Calculate the following: n equals 5, surveying 5 people at a time. Letter 1D465. Equals. S equals. Draw a smooth curve through tops of the bars of the histogram. Use 1 to 2 complete sentences to describe the general shape of the curve. Discussion questions. Why did the shape of the distribution of the data change as n changed? Use 1 to 2 complete sentences to explain what happened. In the section titled Collect the Data, what was the approximate distribution of the data? X. In the section titled Collecting Averages of Groups of 5, what was the approximate distribution of the averages? Letter 1D44B. In 1 to 2 complete sentences, explain any differences in your answers to the previous 2 questions. Stats Lab. Central Limit Theorem, Cookie Recipes. Class Time Names. Student Learning Outcomes. The student will demonstrate and compare properties of the central limit theorem. Given x equals length of time, in days, that a cookie recipe lasted at the Olmsted homestead. Assume that each of the different recipes makes the same quantity of cookies. Recipe X, recipe X, recipe X, recipe X. 1 1 16 2 30, 1 3 46 2. 2 5 17 2 32, 4 47 2. 3 2 18 4 33 5 48 11. 4 5 19 6 34 6 49 5. 5 6 21 35 6 55. 6 1 21 6 36 1 51 4. 7 2 22 5 37 1 52 6. 8 6 23 2 38 2 53 5. 9 5 24 5 39 1 54 1. 10 2 25 1 46 55 1. 11 5 26 6 40 1 1 56 2. 12 1 27 4 42 6 57 4. 13 1 28 1 43 2 58 3. 14 3 29 6 44 6 59 6. 15 2 32 45 2 65. Table 7. 4. Calculate the following: Mux equals. Sigmax equals. Collect the data. Use a random number generator to randomly select 4 samples of size n equals 5 from the given population. Record your samples in Table 7.5. Then, for each sample, calculate the mean to the nearest tenth. Record them in the spaces provided. Record the sample means for the rest of the class. Complete the table. Sample 1, Sample 2, Sample 3, Sample 4, Sample means from other groups. Means. Letter 1D465 equals letter 1D465 equals letter 1D465 equals letter 1D465 equals Table 7. 5. Calculate the following. Letter 1D465 equals S letter 1D465 equals. Again, use a random number generator to randomly select 4 samples from the population. This time, make the samples of size n equals 10. Record the samples in Table 7-6. As before, for each sample, calculate the mean to the nearest tenth. Record them in the spaces provided. Record the sample means for the rest of the class. Sample 1, Sample 2, Sample 3, Sample 4, Sample means from other groups. Means, letter 1D465 equals letter 1D465 equals letter 1D465 equals letter 1D465 equals Table 7. 6. Calculate the following. Letter 1D465 equals S letter 1D465 equals. For the original population, construct a histogram. Make intervals with a bar width of 1 day. Sketch the graph using a ruler and pencil. Scale the axes. This is a blank graph template. The horizontal axis is labeled time, days, and the vertical axis is labeled frequency. Figure 7. 13. Draw a smooth curve through the tops of the bars of the histogram. Use 1 to 2 complete sentences to describe the general shape of the curve. Repeat the procedure for n equals 5. For the sample of n equals 5 days averaged together, construct a histogram of the averages, your means together with the means of the other groups. Make intervals with bar widths of 12. A day, sketch the graph using a ruler and pencil. Scale the axes. This is a blank graph template. The horizontal axis is labeled time, days, and the vertical axis is labeled frequency. Figure 7.14. Draw a smooth curve through the tops of the bars of the histogram. Use 1 to 2 complete sentences to describe the general shape of the curve. Repeat the procedure for n equals 10. For the sample of n equals 10 days averaged together, construct a histogram of the averages, your means together with the means of the other groups. Make intervals with bar widths of 12. A day, sketch the graph using a ruler and pencil. Scale the axes. This is a blank graph template. The horizontal axis is labeled time, days, and the vertical axis is labeled frequency. Figure 7.15. Draw a smooth curve through the tops of the bars of the histogram. Use 1 to 2 complete sentences to describe the general shape of the curve. Discussion questions. Compare the 3 histograms you have made, the 1 for the population and the 2 for the sample means. In 3 to 5 sentences, describe the similarities and differences. State the theoretical according to the CLT distributions for the sample means. N equals 5, letter 1D465. N equals 10, letter 1D465. Are the sample means for n equals 5 and n equals 10 close to the theoretical mean mux? Explain why or why not. Which of the 2 distributions of sample means has the smaller standard deviation? Why? As n changed, why did the shape of the distribution of the data change? Use 1 to 2 complete sentences to explain what happened.